Look up at the night sky, and what do you see? A scattering of stars, the faint glow of distant galaxies, beauty beyond words. But here's the astonishing truth. Everything visible, everything we've ever observed with telescopes, accounts for less than 5% of the universe. The rest is shrouded in darkness, dominated by an invisible force so mysterious. It defies detection yet holds galaxies together like an unseen hand. This is dark matter, the universe's greatest enigma, and at the heart of this mystery lie the colossal structures known as dark matter halos, vast, ghostly cocoons that envelop galaxies, dictating their fate while remaining utterly hidden from our eyes. Imagine a puppeteer pulling strings in the shadows, unseen but undeniable in its influence. That's what dark matter halos do. They shape the cosmos on a scale so grand, entire galaxies dance to their tune. Without them, stars would scatter, spirals would unravel, and the universe as we know it would cease to exist. Yet despite their monumental role, these halos refuse to reveal themselves. They don't emit light, they don't reflect it, they're cosmic phantoms, detectable only by the gravitational fingerprints they leave behind. How can something so fundamental remain so elusive? And what other secrets do these invisible giants hide? That's the journey we're embarking on today, a deep dive into 25 mind-bending mysteries of dark matter halos. From their bizarre gravitational quirks to their role in the birth of galaxies, we'll explore how these unseen architects shape the universe in ways that challenge everything we think we know. Some of these puzzles may never be solved in our lifetime, but that's what makes them so thrilling, because every question leads us closer to unraveling the true nature of reality itself. So let's step into the shadows and uncover the secrets of the cosmic dark matter halo, one astonishing revelation at a time. Picture a mountain made of shadow, so massive it bends space around it, yet completely invisible to your eyes. That's the eerie reality of dark matter halos. These cosmic titans can weigh 1 trillion times more than our sun, yet they pass through ordinary matter like ghosts through walls. How is that possible? The answer lies in what they're made of, or rather, what they're not made of. Dark matter doesn't behave like anything we're familiar with. It doesn't collide with atoms, it doesn't glow or flicker, and it doesn't even slow down. It's as if the universe built these halos from an entirely different rulebook, one we're only beginning to decipher. Think of a spiderweb glistening with dew. You can't see the silk threads from a distance, only the way they pull droplets into delicate patterns. Dark matter halos work the same way. We can't spot them directly, but we can see their gravitational handiwork. Stars on the outskirts of galaxies whirl faster than they should, as if tugged by unseen ropes. Galaxies cluster together in vast filaments, forming a cosmic web that shouldn't hold its shape without some invisible scaffolding. Even light itself bends around these phantom halos, warping our view of distant stars like a funhouse mirror. The universe is practically shouting at us, something's here, but when we reach out to touch it, our hands close on empty space. Here's where it gets even stranger. If dark matter halos are so enormous, why haven't we found a single particle of what they're made of? Scientists have built detectors deep underground, shielded from cosmic noise, waiting for the faintest whisper of a dark matter collision. They've sent satellites scanning the skies for mysterious gamma-ray flashes that might betray its presence. So far, silence. It's like trying to catch smoke with your bare hands. Some theories suggest dark matter could be WIMP, weakly interacting massive particles, while others propose it's made of actions, particles so light they flow through the cosmos like a faint, intangible breeze. But until we catch one in the act, these halos remain the universe's ultimate vanishing act. Yet perhaps the most mind-bending part isn't their invisibility, it's their permanence. Ordinary matter clumps, burns, and fades, but dark matter halos are nearly indestructible. they've survived cosmic collisions that shred galaxies apart, emerging unscathed like shadows after a storm. They might be the oldest structures in existence, primordial blueprints from the dawn of time, silently guiding the birth of every star and planet we'll ever know. And that's the heart of the mystery, how something so vast, so ancient, and so essential to the fabric of reality can still hide in plain sight. Even the most sophisticated cosmic predictions sometimes clash with reality, and nowhere is that more baffling than in the case of the missing satellites. Here's the puzzle. Our best simulations of dark matter halos suggest the Milky Way should be surrounded by hundreds, even thousands, of tiny satellite galaxies, each tethered to its own small halo. Yet when astronomers count them, only a few dozen show up. It's as if someone erased 3/4 of the universe's galactic neighborhood, leaving behind empty space where bustling cosmic communities ought to be. One explanation could lie in the very nature of dark matter itself. What if it's not entirely cold, as most theories assume? Cold dark matter moves sluggishly, clumping easily into halos of all sizes. But if dark matter particles are slightly warmer, zipping through space with more energy, they might resist forming those countless tiny halos, leaving fewer satellites behind. Imagine trying to build a sandcastle with dry, loose grains versus damp, sticky sand. The warmer version simply wouldn't hold together as well, potentially solving the missing satellite mystery at its root. Then again, maybe the satellites aren't missing at all, just hiding. Many of these galaxies could be so faint, so drowned in starlight that our telescopes simply overlook them. Recent discoveries of ultra-dim dwarf galaxies, some with only a few hundred stars, hint at a hidden population lurking in the shadows. It's like realizing the quiet kid in the back of the classroom has been scribbling genius equations all along. We just weren't paying close enough attention. But here's where it gets controversial. Some scientists argue the problem isn't with dark matter or our instruments, but with the simulations themselves. Could the models be oversimplifying how galaxies form inside halos, or underestimating how harsh cosmic environments strip away fragile satellites? Others propose wilder ideas, like primordial black holes or even exotic dark matter interactions. The debate rages on because every potential solution opens new questions. What's certain is this: the missing satellites aren't just a counting error. They're clues. Whether the answer reshapes our understanding of dark matter or reveals hidden corners of the cosmos, one thing's clear: the universe still has plenty of surprises up its sleeve. The center of a dark matter halo should be the easiest place to find it, the deepest part of the gravitational well, where invisible particles ought to pile up like snow in a valley. But when scientists peer into the hearts of galaxies, they're met with a glaring contradiction. Simulations insist these halos must have dense, spiky centers, what astronomers call cusps, where dark matter concentrations skyrocket toward the core. Yet real-world observations tell a different story. Many galaxies appear to have smoother, flatter cores, as if someone took a cosmic spatula and leveled out the peak. This mismatch between theory and reality is the Cusp-Core problem, and it's been gnawing at astrophysicists for decades. Picture a mountain with a needle-sharp summit versus one with a rounded, rolling top. That's the difference between what computers predict and what telescopes actually see. The sharp cusps should form naturally if dark matter is cold and collisionless, as most models assume. Particles would swarm inward, pulled by gravity, stacking up in a steep, dense spike. But when astronomers measure the motion of stars and gas in dwarf galaxies, ideal test cases, since dark matter dominates them, the data often points to gentler gradients, more like a hill than a spire. It's as if something's been churning the dark matter, smoothing out the center against all expectations. So where does the disconnect come from? One leading theory suggests dark matter might not be entirely solitary. If particles can interact with each other not just through gravity but through some unknown force, they could scatter like billiard balls, redistributing energy and flattening the central cusp. This self-interacting dark matter would act like a cosmic mixer, smoothing out the halo's core over billions of years. Imagine a crowded dance floor where everyone avoids touching until suddenly they don't. The motion changes, the crowd spreads, and the density evens out. But there's another twist. Ordinary matter might be the culprit. Baryonic feedback, the push and pull of stars, gas, and supernova could be stirring the pot. When massive stars explode, their violent outflows might shove dark matter around, like a plunger rippling through water. Some simulations now include these effects, and remarkably, they sometimes produce those smoother cores naturally. It's a reminder that dark matter doesn't exist in isolation. It's locked in a dynamic dance with the visible universe, and every step leaves a mark, yet the debate is far from settled. Not all galaxies defy the cusp prediction. Some, like the Milky Way's faint companions, still align with the classic model. Others, like the iconic Dragonfly 44, a ghostly galaxy made almost entirely of dark matter, deepen the mystery with cores so diffuse they barely register. Could the truth lie in a combination of factors, or does dark matter behave differently in different cosmic environments? Every observation adds another piece to the puzzle, but the full picture remains just out of reach. What makes this controversy so thrilling is its stakes. If dark matter truly interacts with itself or responds strongly to baryons, it's not just a tweak to the theory, it's a revolution. We'd be staring at a whole new chapter in physics, one where the invisible majority of the universe is far more complex, far more dynamic than we ever imagined. Until then, the Cusp-Core problem stands as a humbling reminder. Even our best simulations are just sketches of a reality we're still learning to see. If dark matter halos are the universe's invisible scaffolding, then dwarf galaxies should be the perfect test cases, small, faint, and dominated by these mysterious structures. But when scientists compare the halos in their supercomputer simulations to the real dwarfs we observe, something doesn't add up. The simulations predict countless massive, dense halos lurking around galaxies like the Milky Way, halos so enormous they should host bright, bustling dwarf galaxies. Yet when we look, we find far fewer dwarfs than expected, and those we do see are often shockingly dim and diffuse. This clash between prediction and reality is the too big to fail problem, and it's forcing astronomers to rethink how galaxies form in the first place. Think of it like a cosmic real estate crunch. Imagine building 100 skyscrapers only to find that just a handful have tenants, and even those are barely occupied. The halos are the skyscrapers, towering and sturdy, but the galaxies inside them are like ghost towns. Why aren't these massive halos brimming with stars as they should be? One possibility cuts to the heart of galaxy formation itself. Maybe these halos did try to build galaxies, but something stopped them. Enter the brutal physics of star formation. Gas collapsing into a halo needs to cool and condense to ignite stars. But in the early universe, fierce ultraviolet radiation from the first galaxies might have heated that gas to oblivion, leaving it too hot to settle. Like trying to light a candle in a hurricane, even if some gas clung on, supernova explosions could have blasted it away before stars could form in earnest. The result, a halo massive enough to host a grand dwarf galaxy, left with only a wisp of stellar stragglers. But there's another twist. What if some of these failed halos are out there just invisible? Astronomers have begun uncovering a shadow population of ultra-faint dwarfs, galaxies so dim they're barely detectable. Some, like Segway 1, contain just a few hundred stars lost in a halo millions of times more massive. It's like finding a single flickering lamp in a stadium built for thousands. These ghostly dwarfs might be the missing link, proving the halos are there, they're just not what we expected. Then again, maybe the simulations themselves are missing a crucial ingredient. Dark matter halos don't exist in a vacuum, they're part of a dynamic, evolving universe. Tidal forces from larger galaxies could have ripped apart nascent dwarfs, stripping away their stars while leaving the halo intact. Or perhaps dark matter isn't as cold as models assume, with particles just energetic enough to resist clumping into the densest halos. Each explanation opens new doors and new questions. What makes this puzzle so fascinating isn't just the mystery of the missing dwarfs, but what it reveals about the delicate balance of cosmic evolution. Galaxy formation isn't just about gravity's pull, it's a battle against radiation, turbulence, and time. Every failed halo is a fossil of that struggle, a reminder that the universe doesn't always build what we predict. And that's the beauty of the too big to fail problem. It's not a flaw in our theories, but a signpost pointing toward deeper truths we've yet to uncover. Gravity should scatter satellite galaxies like marbles tossed onto a table, random, chaotic, orbiting in all directions. Yet when astronomers mapped the Milky Way's satellite galaxies, they found something bizarre. Many of them orbit in a razor-thin plane, like bees circling a hive in perfect formation. This isn't just a quirk of our galaxy. Andromeda, our closest galactic neighbor, shows the same strange alignment, its satellites dancing in a disk so flat it defies the odds. According to dark matter halo simulations, this shouldn't happen. Halos are supposed to be roughly spherical, with satellites scattered in all directions like a cloud of gnats. So why do real galaxies flout the rules? One explanation might rewrite galactic history. These thin planes could be fossils of the universe's youth, relics from when galaxies first formed. Picture a spinning pizza dough flattening as it stretches. Gas and dark matter in the early universe might have collapsed into vast, rotating sheets, channeling satellites into these aligned orbits billions of years ago. If true, these planes are cosmic time capsules, preserving the motions of a younger, more orderly universe. But here's where it gets contentious. Some scientists argue these planes are just illusions, statistical flukes in a universe full of randomness. Flip a coin enough times and you'll eventually get 10 heads in a row. Could the same principle apply to satellite galaxies? Maybe, but the odds of both the Milky Way and Andromeda having such striking planes by chance are astronomically low. It's like finding two snowflakes with identical patterns possible, but unlikely enough to demand another explanation. Then there's the dark matter twist. If halos are as dynamic as some theories suggest, their gravitational tides could have sculpted these planes over time. Imagine a whirlpool dragging leaves into a spiral. Dark matter's invisible currents might have herded satellites into these peculiar orbits. Or perhaps dark matter isn't completely dark. If it interacts even faintly with itself or with ordinary matter, those subtle forces could nudge satellites into alignment, like magnets arranging iron filings. The debate rages because the stakes are high. If these planes are real and not random, they hint at gaps in our understanding of dark matter's behavior, or even flaws in our cosmic simulations. Every time we think we've pinned down the rules of the universe, galaxies throw us a curveball, and that's the beauty of the plane of satellites mystery. It's not just about where these tiny galaxies orbit, but what their paths reveal about the invisible hands guiding them. Take two seemingly identical galaxies, same size, same amount of stars and gas, and you'd expect their dark matter halos to behave similarly, right? Yet when astronomers measure how these galaxies rotate, the results can be shockingly different. Some spiral galaxies have stars whipping around their cores at breakneck speeds, their rotation curves staying flat far beyond where visible matter should allow. Others, with nearly identical stellar content, show rotation curves that plummet unexpectedly, as if their dark matter halos forgot to show up for work. This isn't just a minor discrepancy, it's a full-blown cosmic identity crisis, revealing just how little we understand about the relationship between ordinary matter and the invisible halos that supposedly dominate galaxies. At the heart of this mystery lies something called the halo-mass concentration relation, a fancy term for how densely packed a dark matter halo is expected to be based on its total mass. In theory, more massive halos should have matter spread more diffusely, like a sprawling cloud, while smaller ones ought to be denser, like tightly packed snowballs. This relationship is baked into our simulations, a fundamental prediction of how dark matter should behave, but real galaxies, they laugh at these rules. Some low-mass galaxies have rotation curves suggesting halos far more concentrated than models allow, while certain heavyweights seem to have bizarrely underweight halos. It's as if dark matter has a mind of its own, refusing to follow the cosmic playbook. So what's throwing the system off? One clue might lie in the chaotic history of galaxy formation. Halos aren't static, they grow over billions of years through mergers and accretion, like snowballs rolling downhill, gathering material. But if a galaxy forms stars explosively early on, supernova winds could blow out gas, stripping away the raw material for future stars and leaving the halo puffed up and less concentrated than expected. Meanwhile, a late-blooming galaxy might retain more gas, funneling it inward and dragging dark matter along for the ride, compressing the halo into a denser configuration. Timing, it seems, might be everything. Then there's the wild card of baryonic physics, the way ordinary matter interacts with its shadowy counterpart. Dark matter halos don't exist in isolation, they're shaped by the galaxies within them. When stars form, explode, or eject gas, the gravitational turbulence can rearrange the halo itself, like a sculptor chiseling away at invisible marble. Some simulations now suggest that feedback from supermassive black holes might even heat dark matter, preventing it from settling into the dense cores models predict. The result, a galaxy that on paper should have a textbook rotation curve, ends up defying expectations because its dark matter got stirred up by cosmic forces we're only beginning to map. But perhaps the most tantalizing possibility is that dark matter isn't as simple as we thought. What if it comes in multiple flavors, some particles more prone to clumping, others more likely to spread out? Or what if it interacts with itself through some unknown force, creating halos with wildly different internal structures despite similar masses? The diversity of rotation curves could be the first hint of a richer dark matter landscape, one where one size fits all no longer applies. Every galaxy's rotation curve is a fingerprint, a unique imprint of its dark matter halo's hidden story. And right now, those stories are telling us something startling. The universe's invisible scaffolding is far more complex, far more dynamic than our best theories can explain. Until we crack this code, the diversity of rotation curves stands as both a challenge and an invitation to look deeper, think differently, and embrace the beautiful chaos of the cosmos. The Milky Way isn't just a swirling disk of stars and gas. It might be hiding a shadowy twin. Imagine an invisible mirror of our galaxy's luminous spiral, a second disk woven from pure dark matter, lurking beneath the stars we see. This is the dark disk hypothesis, a tantalizing idea that could rewrite where and how we hunt for dark matter's elusive particles. Most simulations assume dark matter halos are roughly spherical, like a colossal cloud enveloping the galaxy. But what if the Milky Way's halo isn't just a featureless blob? If dark matter interacts ever so slightly with itself or with ordinary matter, the gravitational tug of the galaxy's rotating disk could have dragged particles into a flattened plane over billions of years. Picture a spoon stirring honey. The dense, sticky liquid eventually settles into the spoon's motion. In this case, the honey is dark matter, and the spoon is the Milky Way's relentless spin. The result, a dark disk, razor-thin and invisible, spinning in sync with the stars but weighing as much as all of them combined. Why does this matter? Because it could explain why dark matter detection experiments keep coming up empty. Most detectors are designed to catch particles streaming from all directions, like rain falling from the sky. But if dark matter is concentrated in a disk, it's more like a horizontal gust requiring us to aim our instruments sideways, not up. Miss the angle and you miss the signal entirely. It's like setting up a net to catch birds but forgetting they migrate in a specific corridor. The evidence for this shadowy structure is subtle but compelling. Studies of stellar kinematics, the way stars move, reveal bizarre gravitational tugs that a spherical halo can't fully explain. Some stars bob up and down through the galactic plane faster than expected, as if something massive but unseen is pulling them back like a cosmic trampoline. Other stars show peculiar velocity patterns, their paths hinting at the gravitational fingerprint of a dense, flattened mass. It's as if we're seeing ripples on a pond but can't spot the stone that caused them. Not everyone's convinced, though. Critics argue the stellar data could be explained by ordinary matter, thick clouds of gas, rogue black holes, or even the Milky Way's central bar. Others point out that forming a dark disk requires just the right amount of interaction. Too much, and dark matter would clump into stars, or collapse. Too little, and it would never settle into a disk at all. It's a cosmic Goldilocks problem, balancing on a knife's edge of physics. Yet the stakes couldn't be higher. If the dark disk exists, it's not just a curiosity, it's a game changer. Direct detection experiments might need to recalibrate their searches, and our understanding of galactic evolution would take a radical turn, even more thrilling. This could be the missing link between dark matter's theoretical predictions and the real, dynamic universe we observe, because sometimes the most profound truths don't blaze in the light, they hide in the shadows, waiting for us to look at just the right angle. Galaxies are supposed to follow certain rules. More stars mean more gravity, more light, more substance. But what if you stumbled upon a cosmic ghost, a galaxy so faint it's nearly invisible, yet somehow holding itself together against all odds? Meet Dragonfly 44, an ultra-diffuse galaxy that shouldn't exist. This wispy collection of stars is so sparse you could fly a spaceship through it for millennia without spotting a single sun. Yet its gravitational grip is so strong it rivals the Milky Way. The reason? A dark matter halo so colossal it defies logic, outweighing the galaxy's visible matter by a staggering 10,000 to 1. This isn't just a quirky exception, it's a cosmic rebellion. Ultra-diffuse galaxies like Dragonfly 44 force us to question everything we thought we knew about how galaxies form. Imagine building a skyscraper with tissue paper and expecting it to withstand a hurricane. That's the equivalent of what these galaxies are doing. Their stars are so few, so scattered, that without an unseen anchor, they should have drifted apart eons ago. Yet here they are, clinging to existence in near darkness, their dark matter halos acting like invisible steel frames. How do such fragile galaxies end up with halos this massive? One theory takes us back to the universe's chaotic youth. Picture a massive dark matter halo forming early on, a gravitational trap waiting to catch gas and birth stars. But what if that gas was stolen? Nearby galaxies or violent supernova could have ripped away the raw material, leaving the halo intact but starved of stars, a skeleton without flesh. Alternatively, these galaxies might be the survivors of brutal tidal encounters, their outer stars stripped away by passing giants, leaving only their dense cores and their monstrous halos behind. Then there's the dark matter twist. If dark matter particles interact even faintly with each other, halos could form with wildly different densities, explaining why some galaxies end up with far more invisible mass than their starlight suggests. Dragonfly 44's halo might be a relic of this hidden physics, a clue that dark matter isn't just a passive spectator but an active sculptor of galactic fate. But the real shocker, these galaxies might be everywhere. Telescopes are uncovering more ultra-diffuse galaxies in clusters and voids, some with barely any stars at all. Their sheer existence challenges our most basic assumptions. If dark matter halos can exist nearly empty, what stops the universe from being littered with invisible halos, unseen and waiting? It's like realizing the ocean is full of icebergs, but most are submerged, invisible to the eye. Ultra-diffuse galaxies aren't just oddities, they're stress tests for dark matter itself. Every time we find one, it's as if the universe is whispering, "You're missing something." Whether it's unseen forces, alternative gravity, or a darker, richer story of cosmic evolution, these ghostly galaxies are holding up a mirror to our ignorance, and the reflection is breathtaking. The Milky Way and Andromeda are cosmic neighbors destined to collide billions of years from now. These two spiral giants will merge in a slow-motion dance. But here's the catch. According to the motions we observe today, this titanic encounter should have already happened. That's the timing argument paradox, a celestial clock that's ticking all wrong, forcing us to question whether we've misunderstood dark matter halos or gravity itself. Measurements show Andromeda barreling toward us at around 110 kilometers per second. Factor in the gravitational pull of both galaxies' dark matter halos, those vast, invisible cocoons that should be accelerating their approach, and simple orbital math suggests they've had more than enough time to meet. Yet here we are, still billions of years apart. It's like watching two magnets hurling toward each other, only to inexplicably slow down mid-flight. So where's the miscalculation? One possibility cuts to the core of dark matter theory. Maybe the halos aren't as massive as we think. If the Milky Way and Andromeda's dark matter is spread more thinly, their gravitational grip would weaken, delaying the collision. But this clashes with other evidence, like the rapid orbits of satellite galaxies that demand hefty halos. You can't have it both ways unless dark matter behaves differently on galactic scales than in our models. Enter the controversial alternative, modified gravity. Theories like modified Newtonian dynamics propose that we don't need dark matter at all, just a tweak to how gravity operates at vast distances. In this framework, the timing mismatch vanishes because galaxies move according to rewritten rules, no invisible halos required. Picture a play where the actors change their choreography mid-scene. Suddenly, the timing makes sense, but only because the director threw out the original script. Yet MUND has its own headaches. It struggles to explain cosmic phenomena like the bullet cluster, where colliding galaxies seem to separate from their gravitational influence, precisely what dark matter predicts. Meanwhile, traditionalists argue the timing paradox could resolve if Andromeda's trajectory isn't perfectly radial. A slight sideways motion could mean it's not headed straight for us, buying extra time before the merger. The debate isn't just academic. If dark matter halos are lighter or shaped differently than simulations suggest, it could mean our entire cosmic web is woven from threads we've yet to measure. Or worse, that we're missing a fundamental piece of physics. The timing argument isn't just a puzzle. It's a ticking clock counting down to a revelation about how galaxies and gravity itself truly work. Dark matter halos are supposed to follow a cosmic hierarchy, massive ones diffuse and sprawling, smaller ones dense and compact. It's a rule etched into our simulations, a fundamental prediction of how these invisible structures should behave. But the universe, as usual, has other plans. When astronomers measure real halos, they find bizarre outliers, some small halos shockingly under-concentrated, others inexplicably overpacked, like suitcases that refuse to follow weight limits. This is the halo mass concentration tension, a glaring mismatch between theory and observation that's forcing scientists to question whether dark matter plays by the rules we've written for it. Take a tiny dwarf galaxy, for instance. According to cold dark matter theory, its halo should be a tightly wound knot of invisible mass, its gravity fierce and unyielding. Yet some dwarfs rotate as if their halos are barely there, their stars moving sluggishly through space like swimmers in thin syrup. Meanwhile, other small galaxies whip around at speeds that demand halos denser than simulations allow, as if their dark matter has been crammed into a cosmic pressure cooker. It's not just a minor discrepancy, it's a full-blown rebellion against the expected order. So what's throwing the system into chaos? One possibility is cosmic variance, the idea that the universe loves exceptions. Halos don't form in isolation. They're sculpted by their environments, like trees shaped by wind. A halo born in a turbulent region, bombarded by galactic neighbors or drowned in scorching intergalactic gas, might end up stretched and puffed out, its density diluted. Another halo, nurtured in a quiet cosmic backwater, could retain its primordial compactness, untouched by the violence around it. The result, a wild spectrum of concentrations that no single rule can explain. But there's a more provocative explanation. What if cold dark matter isn't so cold after all? The cold in cold dark matter means particles move sluggishly, clumping easily into dense halos. But if dark matter has even a hint of warmth, if particles zip around with a bit more energy, they could resist piling up as tightly, solving the overconcentration problem at a stroke. It's like trying to pack snowballs versus wet sand. One holds its shape, the other slips through your fingers. Some theories even suggest dark matter might be fuzzy, made of ultra-light particles that behave more like waves, smoothing out halos into gentler profiles. Yet the plot thickens when baryons, ordinary matter, enter the mix. Stars and gas aren't just passive residents, they're active participants, reshaping their halos through supernova explosions, galactic winds, and the gravitational tug-of-war of spiral arms. A burst of star formation can blast gas outward, dragging dark matter with it and fluffing up the halo's core. Conversely, a quiet galaxy might let its dark matter settle undisturbed, preserving its primordial density. This intricate feedback loop means no two halos evolve alike, turning the mass-concentration relationship into a cosmic fingerprint, unique, messy, and gloriously unpredictable. The tension isn't just a technical hiccup, it's a window into dark matter's true nature. Every outlier halo, every deviation from the expected curve is a clue. Maybe dark matter interacts with itself in ways we haven't imagined, or maybe gravity itself needs rethinking at galactic scales. Until we solve this puzzle, the mass concentration tension stands as a humbling reminder. The universe's invisible architecture is far stranger, far more dynamic than our tidy models can contain. There's a cosmic crime seen a billion light-years away, and the evidence points to an invisible culprit. The bullet cluster, a violent collision of two galaxy clusters, is often hailed as definitive proof of dark matter's existence. Here's why. When these clusters smashed together, their hot gas clouds, visible in X-rays, slowed down and piled up at the center like cars in a traffic jam. But something else kept racing ahead: the galaxies themselves, along with their gravitational pull. The twist: most of that gravity wasn't coming from the galaxies or the gas. It was coming from nothing, or rather from dark matter streaming through the wreckage unfazed, leaving behind gravitational fingerprints that bend the light of distant stars like a funhouse mirror. This cosmic detective story seems airtight until you notice the loopholes. If dark matter is ghostly enough to pass through the collision without a scratch, why doesn't it just breeze through Earth undetected? Why do our underground detectors sit silent, waiting for a particle that refuses to show? And why, in other merging clusters, do the gravitational hotspots sometimes align suspiciously with the gas exactly where dark matter shouldn't be? The bullet cluster might be smoking gun evidence, but the bullet itself is still missing. Enter the rebels, modified Newtonian dynamics, or MUND, a theory that ditches dark matter entirely and tweaks gravity instead. MUND argues that the bullet cluster's gravity map isn't proof of invisible mass, just gravity behaving oddly at vast scales. It's like realizing you've been misreading a compass all along. Maybe the needle points differently when you're crossing cosmic distances. Yet MUND stumbles when faced with the universe's full menu of clusters. Some mergers split gravity from matter cleanly, like the bullet cluster, but others tangle them in ways MUND can't easily explain. It's as if the universe is mixing the rules mid-game, leaving theorists scrambling to adapt. The real kicker: both sides might be half right. Imagine dark matter that doesn't just sit there, it interacts, however faintly, with itself or with ordinary matter. A whisper of collision, a nudge of friction, could explain why some clusters separate neatly while others blur. Or perhaps dark matter isn't one thing but many, a hidden zoo of particles with different quirks. The bullet cluster, then, isn't just proof, it's a provocation, a challenge to dig deeper. Because in the end, even our best cosmic evidence comes with shadows of doubt, and those shadows might be where the truth is hiding. Every galaxy spins, a graceful whirl of stars, gas, and dust that gives the universe its mesmerizing spirals and swirling disks. But here's the cosmic twist. According to simulations, the dark matter halos enveloping these galaxies should be spinning too, their angular momentum aligned with the galaxies they cradle. Except they're not. Observations reveal a glaring mismatch, a disconnect so puzzling it forces us to question how galaxies and their invisible halos even form in the first place. This is the dark matter halo spin mystery, and it's tearing a hole in our understanding of cosmic evolution. Picture a figure skater pulling their arms in, spinning faster as they compact. That's how angular momentum works: conserved, transferred, amplified. When galaxies form, the same physics should apply. As gas collapses into a dark matter halo, it's supposed to share the halo's spin, eventually settling into a rotating disk that mirrors the halo's motion. But reality paints a different scene. Many galaxies spin at odd angles to their halos, some even counter-rotating, like a record spinning backward on its turntable. How does this happen? Where does the angular momentum go? Or more pressingly, where does it come from? The answer might lie in the chaos of galaxy formation itself. Halos don't grow in isolation. They're born from a web of collapsing gas and mergers, a cosmic game of bumper cars where every collision twists and tilts their spin. Imagine stirring a cup of coffee. The swirl you create isn't just from your spoon, but from how the liquid sloshes against the sides. Similarly, as gas funnels into a halo, it doesn't just passively inherit rotation. It interacts, clumps, and sometimes rebels, dragging dark matter along for the ride. Turbulence, magnetic fields, and even supernova explosions could scramble the original spin, leaving galaxy and halo misaligned. But there's a darker possibility. What if halos don't spin as much as we think they should? Simulations assume dark matter is cold, slow-moving, and quick to clump. But if particles have even a hint of warmth or interact in unexpected ways, halos might form with less intrinsic rotation to begin with. It's like expecting a top to spin smoothly, only to find it wobbles because the weight's uneven. Some theories even suggest dark matter's angular momentum could leak away over time, siphoned off by cosmic filaments or stolen during galactic collisions. The stakes, nothing less than our grasp of galaxy birth. If halos and galaxies spin out of sync, it means the pristine equations we've relied on, those elegant models of gas cooling and disk formation, are missing a critical piece. Maybe baryonic physics is wilder than we guessed, or dark matter more dynamic. Either way, the spin mystery isn't just a wrinkle in the data. It's a flashing signpost pointing toward a deeper, messier truth about how the universe builds its grandest structures. And until we solve it, every spinning galaxy remains a silent challenge to the stories we've told ourselves about the cosmos. Dark matter halos may be invisible, but the ordinary matter within them shouldn't be. Yet when astronomers tally up the expected baryons, the protons and neutrons making up stars, gas, and planets, they find a glaring shortfall. These halos, some weighing trillions of times more than our Sun, appear suspiciously starved of the visible stuff that should account for nearly 20% of their mass. It's as if the universe misplaced an entire cosmic pantry's worth of ingredients, leaving scientists scrambling to figure out where the baryons went, or if they were ever there at all. The math is straightforward. Based on the cosmic ratio of dark matter to baryons established by the Big Bang's afterglow, every massive halo should cradle a hefty reservoir of ordinary matter. But observations tell a different story. Galaxies like the Milky Way, for instance, host only a fraction of the expected baryons, with stars and cold gas making up less than 10% of the predicted total. Even adding in the diffuse gas between stars barely nudges the needle. So where's the rest? The answer might lie in the universe's most overlooked real estate, vast, searing hot clouds of gas hiding in plain sight. Imagine turning up the thermostat until water vapor becomes invisible. That's the trick these missing baryons are pulling. At temperatures reaching millions of degrees, gas emits X-rays rather than visible light, blending into the background like steam in a sauna. Satellite telescopes like Chandra have caught glimpses of this ultra-hot plasma weaving through galaxy clusters, but isolating it around individual halos is like trying to spot a candle in a bonfire. Some of these baryons could be lurking in extended coronas around galaxies, too faint and diffuse to detect. Others might be strung along cosmic filaments, the sprawling highways of gas connecting galaxy clusters, too thin to register with current instruments. But there's another twist. Baryons might not be missing at all, just transformed. Supermassive black holes at galactic centers act like cosmic shredders, swallowing gas and blasting it outward in turbulent winds. These energetic outflows could push baryons far beyond their host halos, scattering them into intergalactic space where they're nearly impossible to track. Alternatively, intense radiation from early galaxies might have ionized gas so thoroughly it became dark, unable to cool and collapse into visible structures. Picture a chef whisking eggs into a froth. The ingredients are still there, just unrecognizable in their new state. The stakes go beyond bookkeeping. If baryons are truly AWOL, it could mean our understanding of halo formation is fundamentally flawed. Perhaps violent galactic feedback ejects them more efficiently than models predict, or maybe dark matter's gravity isn't as adept at trapping ordinary matter as we assumed. On the other hand, if the baryons are simply hiding in plain sight, their discovery could rewrite the thermal history of galaxies, revealing how energy flows through the cosmic web. Either way, the missing baryon problem isn't just a census discrepancy, it's a clue to how the universe organizes its building blocks and why some of them refuse to be seen. One thing's certain, the universe doesn't lose matter. It just plays hide and seek on a scale we're only beginning to grasp. And until we uncover every last baryon, dark matter halos will keep their most ordinary secret tucked away, right under our noses. Cosmic voids are the universe's ghost towns, vast, nearly empty regions where galaxies are few and far between. These lonely galaxies, adrift in the abyss, should be the perfect place to study pristine dark matter halos, untouched by the gravitational chaos of crowded galactic neighborhoods. Yet when astronomers peer into these voids, they find something startling. Some of these galaxies appear to have little to no dark matter at all. It's as if the universe forgot to pack the very ingredient that's supposed to dominate every corner of space. Take NGC 1052DF2, a galaxy so eerily transparent you can practically see right through it. This wispy collection of stars floating in the cosmic boonies rotates so sluggishly that its visible matter alone could explain its motion, no dark matter required. That shouldn't happen. According to our models, even the most isolated galaxies should be swaddled in hefty halos, their gravity shaping every spin and orbit. So why do these void galaxies seem to defy the rules? One possibility is that void galaxies are cosmic late bloomers. In the dense urban centers of galaxy clusters, halos grow fat on a steady diet of mergers and accretions. But out in the voids where gas is scarce and interactions rare, halos might have starved, never reaching the masses we'd expect. Imagine planting a tree in barren soil. It might survive, but it won't grow as tall as its forest-dwelling cousins. Similarly, these galaxies could have formed in environments so deprived of raw material that their halos remained stunted, barely leaving a gravitational footprint. Then there's the measurement problem. Void galaxies are faint and hard to observe. Their rotation curves often fuzzy at the edges, could we simply be misreading the data? It's possible that what looks like a lack of dark matter is really just our instruments missing subtle signals, like mistaking a whisper for silence. But that doesn't explain cases like DF2, where the numbers are stubbornly clear. This galaxy spins as if it's barely holding itself together, its stars moving in slow, lazy arcs that betray no invisible anchor. Or perhaps the answer lies in the turbulent history of voids themselves. These regions aren't just empty, they're expanding, stretched thin by the universe's accelerating growth. Over billions of years, this stretching might have pulled dark matter away from some galaxies, leaving them stranded in a gravitational vacuum. Picture a boat drifting from its mooring, the rope snapping as the tide carries it out to sea. In this case, the tide is dark energy, and the rope is the tenuous grip of a halo that couldn't keep up. But here's the most tantalizing idea. What if these galaxies did have halos but lost them in a cosmic robbery? Simulations suggest that when small galaxies pass too close to massive neighbors, tidal forces can strip away their dark matter, leaving behind a skeleton of stars. In voids where galaxies are sparse, this seems unlikely, but what if the thief wasn't another galaxy, but the void itself? The relentless pull of expanding space might have siphoned off dark matter over eons, leaving these galaxies oddly bare. Whatever the explanation, void galaxies are more than just outliers, they're stress tests for our theories. If dark matter can vanish from entire galaxies, does that mean it's not as universal as we thought? Or are we seeing the fingerprints of some deeper, unseen physics, where dark matter behaves differently in the universe's loneliest corners? The answers might rewrite not just the story of halos, but the very rules of cosmic evolution. After all, in the silence of the voids, even whispers can sound like thunder. Dwarf galaxies should be the simplest systems in the universe, tiny, uncomplicated collections of stars where dark matter's influence is crystal clear. But when astronomers study these cosmic minnows, they find chaos instead of order. Some dwarfs are drowning in dark matter, their stars whirling at impossible speeds under the grip of unseen halos. Others seem almost empty of it, floating through space like ghost ships with no invisible anchor. This bizarre mismatch is more than just a curiosity. It's a direct challenge to our understanding of how galaxies form and evolve. Take the Fornax dwarf, a satellite of the Milky Way so diffuse its stars barely cling together. Based on its puny luminosity, its dark matter halo should be modest. Yet when scientists measure its gravity, they find a surprising excess, as if someone stuffed an invisible elephant into a tiny closet. Then there's its neighbor, the sculptor dwarf, which follows expectations almost perfectly, its rotation curve tracing the graceful arc predicted by cold dark matter theory. Why do two similar galaxies, born in the same cosmic neighborhood, end up with such radically different dark matter inventories? One explanation lies in the violence of galactic tides. When a dwarf galaxy orbits too close to a massive parent like the Milky Way, gravitational forces can rip away its outer layers, both stars and dark matter, leaving behind a stripped core. Picture a grapevine picked apart by birds. Some clusters of fruit remain intact, others are plucked nearly bare. This tidal stripping could explain why some dwarfs appear dark matter deficient, their halos whittled down by eons of gravitational harassment. Yet this doesn't account for the outliers like Triangulum 2, a dwarf so rich in dark matter it outweighs its stars by a factor of hundreds. If tides are the sculptor, why do some galaxies emerge from the chaos with their halos not just intact but inexplicably enhanced? The answer might lie in the primordial universe. Dark matter halos didn't form uniformly. Tiny differences in density in the early cosmos could have seeded some regions with clumpier, more concentrated halos than others. These fluctuations, frozen in time, would mean dwarfs were never normal to begin with. Like siblings with the same parents but radically different genetics, their dark matter content could have been set at birth, untouched by later events. But there's a wild card: baryonic feedback. Stars aren't just passive residents, they shape their halos through supernova explosions and stellar winds. In some dwarfs, fierce bursts of star formation might have blasted dark matter outward, puffing up the halo's core. In others, quiet histories left the halo dense and untouched. This delicate interplay between visible and invisible matter could explain the dizzying diversity we see, proof that galaxies, even the smallest ones, are never just products of gravity, but of 1,000 cosmic contingencies. The real lesson here: dwarf galaxies are the universe's way of keeping us humble. Just when we think we've pinned down dark matter's rules, these tiny systems rewrite them. Whether through violence, chance, or some hidden physics we've yet to uncover, they remind us that the cosmos thrives on exceptions, and in those exceptions we might just find the keys to the universe's deepest secrets. Simulations paint a universe teeming with invisible architecture, not just vast dark matter halos, but smaller subhalos nested inside them like cosmic Russian dolls. According to our best models, a galaxy like the Milky Way should host thousands of these substructures, each its own gravitational island. Yet when astronomers scan the skies, they find only a fraction of that number. This isn't just déjà vu of the missing satellites problem, it's something deeper. The halo substructure crisis forces us to confront whether our simulations are overpopulating the cosmos with phantom clumps, or if we're simply missing an entire invisible ecosystem swirling around us. At the heart of the issue lies a paradox of scale. Supercomputer simulations like Via Lactea and Aquarius track dark matter's behavior with astonishing precision, tracing how tiny fluctuations in the early universe snowballed into halos and subhalos of all sizes. These digital universes spawn subhalos by the thousands, some as massive as dwarf galaxies, others no heavier than a star cluster. But when telescopes peer into our galactic backyard, the observed satellite count falls woefully short. It's like expecting a bustling metropolis and finding a ghost town instead. One clue might lie in the brutal reality of galactic survival. Not all subhalos get to host visible galaxies. The smallest, weakest ones could have had their gas stripped away by ultraviolet radiation in the universe's fiery youth, leaving them dark and starless, essentially invisible except through gravitational lensing. Imagine a forest where only the tallest trees break through the canopy. The rest linger in shadow, unseen but still shaping the ecosystem. These dark subhalos might be everywhere, their gravitational tug subtly warping the paths of stars or bending distant quasar light, waiting for ultra-sensitive instruments to betray their presence. Then there's the thorny role of baryonic physics. Simulations often treat dark matter as the sole architect, ignoring how ordinary matter, stars, gas, supernova, can reshape halos over time. When baryons are included, the story changes. Supernova explosions might blast subhalos apart before they can form stars, or tidal forces from the Milky Way's disk could shred them into streams. Recent simulations like Eagle and Illustris TNG show that feedback from star formation can heat and disperse dark matter, puffing up subhalos until they're too diffuse to detect. It's a cosmic game of survival where only the toughest structures endure and the rest fade into the background. But the most tantalizing possibility is that dark matter itself is more exotic than we thought. If it's not perfectly cold but slightly warm, with particles moving faster and resisting clumping, the number of small subhalos would plummet. Alternatively, if dark matter interacts with itself, colliding or scattering like particles in a plasma, it could erase substructure like a cosmic eraser, smoothing out pencil marks. These tweaks wouldn't just solve the subhalo problem, they'd rewrite the rules for how all halos form, from the smallest dwarfs to the largest galaxy clusters. The hunt for these missing subhalos is already underway. Some teams search for gamma-ray flares, hints that dark matter particles might be annihilating in dense clumps. Others track perturbations in stellar streams, the delicate rivers of stars torn from globular clusters, which could reveal unseen halos tugging at them like hidden magnets. And then there's gravitational lensing, where subtle distortions in the light of distant galaxies map the invisible scaffolding between us and them. What makes this mystery so gripping isn't just the gap between theory and observation. It's what that gap reveals about our place in the cosmos. If subhalos are truly as abundant as simulations suggest, we're living in a far richer, more textured universe than our eyes can see. And if they're not, then dark matter is stranger still, and the simulations guiding us for decades might need a fundamental rewrite. Either way, the halo substructure problem isn't just a puzzle to solve. It's a reminder that the universe's secrets aren't just hidden in the darkness, but woven into its very fabric. Dark matter halos are often imagined as perfect spheres, vast, invisible bubbles cradling galaxies in their gravitational embrace, but the truth might be far stranger. Simulations suggest these halos could be triaxial, like cosmic potatoes stretched and squished along 3 different axes, or even flattened into disks that spin alongside their galaxies. The problem, we can't see them directly, forcing us to piece together their shapes from gravitational whispers and the subtle warping of spacetime itself. Gravitational lensing offers one of our best windows into this mystery. When light from distant galaxies bends around massive objects, it doesn't just magnify them. It distorts them into arcs and rings, a cosmic funhouse mirror whose twists reveal the hidden mass responsible. Lensing patterns around galaxy clusters like Able 1689 show clear signs of asymmetry, as if the dark matter halos distorting the light aren't spherical at all, but elongated or flattened. It's like trying to reconstruct a sculpture by studying its shadow. The contours hint at something far more complex than a simple ball of invisible matter. Yet simulations muddy the waters. Cold dark matter models tend to produce halos that are triaxial, lopsided, and irregular, like stones smoothed by a river but still rough-edged. But when baryonic matter enters the mix, galaxies forming inside these halos can tug and mold them, rounding out the irregularities into something closer to a sphere. Picture a lump of clay spinning on a potter's wheel. As the wheel turns, centrifugal force flattens the clay into a disk, while the potter's hands the galaxy's gravity smooth it further. The result, halos that might start out triaxial but end up reshaped by the very galaxies they host. Then there's the wild card of mergers. When 2 halos collide, the aftermath isn't a neat sphere but a chaotic, elongated mess like taffy pulled in opposite directions. Some halos might never fully recover, leaving behind fossil distortions that linger for billions of years. Others might relax into equilibrium, but even then, equilibrium doesn't always mean round. The Milky Way's own halo, for instance, might be subtly squashed, its poles flattened by the gravitational influence of the Large Magellanic Cloud as it orbits nearby. The stakes of this debate aren't just academic. Halo shapes influence how galaxies form and evolve. A triaxial halo could funnel gas into strange, unstable orbits, triggering bursts of star formation or starving a galaxy of fuel. A flattened halo, on the other hand, might spin in sync with its galaxy, stabilizing it like a gyroscope. Even the orientation of a halo's axis could determine whether a galaxy grows into a majestic spiral or a chaotic, clumpy monstrosity. So why haven't we settled this yet? Because dark matter refuses to play fair. Every time we think we've pinned down its behavior, the universe throws us a curveball, like ultra-diffuse galaxies that shouldn't exist, or lensing anomalies that defy even the most sophisticated models. The shape of halos isn't just a question of geometry. It's a test of whether we truly understand the invisible scaffolding of the cosmos. Until we do, every new observation is another piece of the puzzle, and another reminder that darkness holds its secrets tight. Imagine 2 dark matter halos with identical masses, same weight, same gravity, seemingly twins. Yet when astronomers observe them, one halo might be bustling with galaxies while its counterpart sits nearly empty, as if the universe played favorites. This bizarre mismatch is the halo assembly bias puzzle, a cosmic quirk proving that when it comes to dark matter, mass isn't the whole story. How these halos formed, when they formed, might hold the key to why the cosmos weaves its invisible fabric so unevenly. Rewind to the universe's earliest epochs. Dark matter didn't clump uniformly. Some regions collapsed faster, their halos assembling in frenzied bursts, while others grew leisurely over billions of years. That timing leaves scars halos born early tangled with the densest knots of the cosmic web, their insides whipped into frenetic motion by constant mergers. Latecomers, meanwhile, formed in quieter neighborhoods, their structures smoother, more serene. That history isn't just trivia, it imprints itself on halos like a birthmark, shaping how they interact with the visible universe. Here's the twist: halos that formed early tend to attract more galaxies, even if they weigh the same as late-forming ones. Picture two magnets with identical strength, one scarred by rough handling, its surface pitted and uneven, the other polished smooth. Dust clings more readily to the rough one. Similarly, early halos, etched by ancient collisions, might offer better footholds for gas to cool and stars to ignite. Their turbulent pasts create gravitational nooks where galaxies can thrive, while late-forming halos, pristine but bland, struggle to hold onto baryons. Yet assembly bias doesn't just affect individual halos, it ripples across the cosmos. Galaxy clusters, those gleaming metropolises of the universe, aren't randomly scattered. They string together along filaments threading the cosmic web, and the glue holding them in place, early forming halos whose gravitational dominance shapes the large-scale structure of everything we see. Late-forming halos, meanwhile, often end up exiled to the voids, the cosmic boonies where galaxies are few and far between. It's a gravitational caste system where birthright determines destiny. The implications are staggering. If assembly bias shapes where galaxies grow, it could explain why some corners of the universe teem with light while others languish in darkness. Simulations that ignore this effect, treating all halos of the same mass as interchangeable, might be missing a critical layer of cosmic history. Like assuming two forests with the same number of trees must harbor identical ecosystems, when in truth, one grew from wildfire ash and the other from floodplains. But the puzzle deepens when we ask why early halos are such overachievers. Does their violent youth leave them with denser cores, better at snagging passing gas? Or do they simply occupy richer environments where the cosmic buffet of matter never runs dry? The answer might lie in the delicate dance between dark matter and ordinary matter, how gas cools, how stars ignite, how feedback from supernovas sculpts the very halos that nurture them. One thing's certain, assembly bias isn't just a footnote in the story of dark matter. It's a plot twist revealing that the universe's invisible scaffolding isn't just about how much stuff is out there, but how and when it all came together. And in that timing, we might finally find the missing link between the halos we can't see and the galaxies we can. Even the smoothest cosmic structures might be fringed with invisible strands, whisper-thin filaments of dark matter stretching from halos like phantom hair. This is the dark matter hair hypothesis, a bold idea suggesting that halos aren't just featureless blobs, but may sprout ultra-dense tendrils, each thinner than a proton but stretching millions of light-years into the void. If real, these filaments could weave the universe into a web far more intricate than we ever imagined, with halos connected by invisible threads that vibrate to the tune of gravity itself. The math behind this idea is as elegant as it is speculative. Just as Earth's gravity creates tidal forces that shape oceans and stretch the moon, dark matter halos might pull streams of particles into filamentary structures, especially around massive objects like black holes. These hairs would be unimaginably dense at their roots, tapering to near nothingness as they extend outward. Picture a comet's tail, but made of pure gravitational potential fluttering in the cosmic wind. Detecting something so ethereal sounds impossible, but gravitational waves might hold the key. When massive objects merge, black holes, neutron stars, they send ripples through space-time that observatories like LIGO can catch. But what if dark matter hairs leave their own faint tremors? As these filaments whip through the cosmos, they could perturb passing gravitational waves, imprinting subtle distortions that next-generation detectors like LISA might one day spot. It's like listening for the rustle of leaves in a hurricane, nearly imperceptible but not quite silent. The implications are staggering. If halos truly grow these phantom strands, they could act as cosmic spider silk, transmitting gravitational forces across vast distances and even funneling dark matter into galaxies faster than traditional models allow. Some theories suggest these filaments might explain why galaxies form stars at unexpected rates, or why certain black holes grow inexplicably massive. They could be the universe's hidden wiring, conducting dark matter's influence in ways we're only beginning to guess. Skeptics, of course, argue that hairs are a bridge too far, an imaginative solution in search of a problem. Without direct evidence, the idea remains in the realm of beautiful speculation. But that's the thrill of cosmology. Sometimes the wildest ideas, tested by the most delicate experiments, reveal truths stranger than fiction. And if LISA or another observatory ever catches a gravitational wave with an odd, hair-like kink, it could be the first hint that the universe's darkness isn't just vast, it's alive with unseen texture. Galaxies and their dark matter halos should grow in lockstep, a cosmic partnership where size matches size. But the universe loves breaking rules, and nowhere is that clearer than in the baffling mismatch between some galaxies and the halos they call home. Take superspirals, galaxies so vast they dwarf the Milky Way, spinning gracefully within halos that, by all accounts, seem too small to hold them. Then flip the script: ultra-compact dwarfs, tiny bundles of stars shackled to halos so massive they could anchor entire galaxies 10 times their size. This isn't just a quirk, it's a full-blown rebellion against the expected order, forcing us to ask, what's really deciding how big a galaxy can grow? The answer might lie in cosmic tantrums, violent outbursts of energy that reshape galaxies from within. Picture a young galaxy, gas flooding into its dark matter halo, primed to birth stars by the billions. But when those stars ignite, some don't just shine, they explode. Supernova blast through the galaxy like fireworks, their shockwaves heating gas and hurling it outward, stripping the fuel for future stars. This feedback can stunt growth, leaving a galaxy smaller than its halo's potential. It's like planting a tree in a giant pot, only to prune its roots every time it tries to grow. In extreme cases, supernova might even eject so much gas that star formation grinds to a halt, leaving a halo mostly empty, a cosmic mansion with barely any furniture. But supernova aren't the only disruptors. Lurking at the heart of many galaxies are supermassive black holes, engines of chaos that can dwarf stellar explosions in sheer destructive power. When these monsters feast on gas, they don't just swallow it quietly. They belch out jets of radiation and plasma at nearly light speed, frying surrounding gas and quenching star formation across entire galaxies. Astronomers call this AGN feedback, short for active galactic nuclei, and it's like a cosmic thermostat, dialing down galaxy growth when the universe gets too rowdy. In some cases, these outbursts might explain why certain halos host galaxies that seem embarrassingly undersized. The black hole didn't just starve the galaxy, it scorched the soil. Yet feedback isn't always a wrecking ball. Sometimes it's a sculptor. Take those super spirals defying expectations. Their secret might be a delicate balance, just enough feedback to keep gas from collapsing too fast, allowing it to funnel smoothly into a sprawling disk without triggering catastrophic bursts of star formation. Think of it as a gardener pruning a bonsai. The right cuts don't weaken the tree, they guide its growth into something elegant and vast. In these galaxies, feedback might be the invisible hand ensuring their halos don't overpack with stars, leaving room for majestic spirals to unfold. The real shock, though, comes when we realize how much hinges on these chaotic processes. Without feedback, galaxies would either devour all their gas too soon, collapsing into dense, stunted blobs, or sprawl uncontrollably, their halos overflowing with stars. The fact that we see neither extreme suggests something extraordinary. The universe self-regulates. Dark matter builds the stage, but ordinary matter, through explosions, radiation, and sheer violence, writes the play. And sometimes that script calls for a galaxy too big or too small for its halo, just to keep things interesting. This discrepancy isn't a flaw in our theories, it's a feature. A reminder that galaxies aren't just products of gravity, but of 1,000 fiery battles between creation and destruction. Every oddball galaxy, every mismatched halo, is a fossil of those battles, a clue to how the universe balances its ledgers. And until we understand that balance, the true story of galaxy growth will remain half-told, waiting in the ashes of supernova and the afterglow of black hole feasts. Dark matter halos are supposed to be frigid, so cold that particles move sluggishly, clumping easily under gravity's pull. But the universe never sticks to the script. Some halos behave like they've been zapped with cosmic caffeine, their particles zipping around with unexpected energy, while others seem unnervingly still, as if frozen in time. This temperature anomaly isn't just a technicality, it's a crack in the foundation of dark matter theory, and the key to unlocking what these halos are really made of. Take the puzzling case of dwarf galaxies. According to cold dark matter models, their halos should be dense and chill, with particles moving at a glacial pace. Yet when astronomers measure the motion of stars within these galaxies, some reveal halos that are oddly warm, their gravitational grip looser than expected. It's like expecting molasses to hold a spoon upright, only to find it's been swapped with lukewarm syrup. Other halos, like those around certain ultra-diffuse galaxies, appear bizarrely cold, so inert they barely seem to interact even with themselves. This split personality might trace back to dark matter's very nature. If halos are made of weakly interacting massive particles, their temperature should be consistent, dictated by their primordial sluggishness. But what if dark matter isn't one thing, but many? Enter action's hypothetical particles so lightweight they behave more like waves than discrete bits of matter. Action like dark matter wouldn't just sit still, it'd ripple and hum, creating halos with subtle variations in temperature. Picture the difference between a frozen lake and a slushy puddle. Both are cold, but one is rigid, the other dynamic. Then there's the wild card of interactions. Most models assume dark matter is loner, indifferent to everything including itself. But if particles occasionally bump or scatter, even faintly, they could exchange energy like dancers in a crowded ballroom. Over billions of years, these microscopic nudges might heat entire halos from within, explaining why some feel warmer than they should. Conversely, halos in quiet cosmic backwaters, untouched by collisions or mergers, could remain unnaturally cold, their particles never stirred into higher energies. The stakes, everything. If halos defy temperature expectations, it could mean dark matter isn't just a passive backdrop but an active participant in cosmic evolution. Warmer halos might resist clumping into dense cores, solving puzzles like the Cusp-Core problem, while colder ones could collapse into ultra-dense knots, seeding bizarre objects like primordial black holes. Even more tantalizing, this anomaly might hint at dark matter's connection to other cosmic mysteries, like the universe's missing baryons or the odd spins of certain galaxies. Yet the real breakthrough will come when we catch these particles in the act. Experiments like ADMS hunt for actions by tuning into their faint electromagnetic whispers, while others probe for WIMP in mild, deep labs. Each anomalous halo, each temperature outlier is a clue, not just to what dark matter is, but how it shapes the universe's grandest structures. And until we solve it, this thermal puzzle remains a smoking gun in the hunt for the cosmos's most elusive architect. Where does a dark matter halo stop and empty space begin? It sounds like a simple question until you realize these invisible giants don't come with edges you can trace with a cosmic highlighter. Unlike galaxies where starlight fades into the void, halos blur into the cosmic web, their boundaries so porous that pinpointing where one ends and another begins is like trying to mark where a cloud's mist turns into clear sky. This is the halo boundary mystery, and it's forcing scientists to rethink how we measure the invisible scaffolding of the universe. The textbook definition points to something called the virial radius, the distance where a halo's gravity finally loses its grip, where matter orbiting within it has just enough energy to balance the pull of dark matter. Imagine swinging a ball on a string. The string's length is your virial radius. Cut it and the ball flies free. For halos, this radius should mark the natural border between structure and chaos. But the universe doesn't do textbooks. In reality, dark matter particles don't suddenly stop at this theoretical line. They thin out gradually, wisping into filaments of the cosmic web like ink dissolving in water. Measuring where this transition happens is maddeningly indirect. Astronomers can't see the halos themselves, so they rely on tracers orbiting galaxies, streams of stars, even the faint distortions of background light to map the invisible mass. But these tracers have limits. Satellite galaxies, for example, might not reach the true outer edges, leaving vast regions uncharted. Meanwhile, gravitational lensing can reveal mass concentrations, but its signal weakens where halos diffuse into the intergalactic void. It's like trying to map a city's outskirts using only the glow of streetlights. Where the lamps stop, your data ends even if the city sprawls farther. Complicating matters is the cosmic web itself. Halos aren't isolated islands, they're knots in a vast net of dark matter filaments, each thread funneling matter into and out of them. Near these filaments, a halo's edge might stretch or warp like a river delta blending into the sea. Some simulations even suggest that halos exchange particles constantly, their boundaries more like busy train stations than fortress walls. This dynamic interplay means a halo's size isn't fixed, it breathes, grows, and shifts over billions of years, defying any single measurement. The stakes here aren't just academic. Misjudging a halo's boundary throws off calculations of its mass, which in turn skews our understanding of everything from galaxy formation to the universe's expansion. Take the Milky Way. If we overestimate our halo's edge, we might assume it weighs more than it does, leading us to overpredict how fast nearby galaxies should orbit us. Conversely, underestimating could hide entire populations of stars or dark matter subhalos lurking just beyond our sight. And then there's the wild card of modified gravity. If dark matter doesn't exist and gravity itself behaves differently at large scales, the whole concept of a halo boundary might be a mirage, a phantom line drawn in sand that the cosmic tide keeps erasing. Either way, the puzzle forces us to confront a humbling truth. Even the universe's most massive structures refuse to be neatly contained. Their edges aren't lines but rhythms, slow, fading whispers in the dark. Deep within every dark matter halo might lie a whisper, an echo of the universe's first moments frozen in time. These invisible structures, spanning hundreds of thousands of light years, could be more than just gravitational traps. They might be cosmic archives preserving details of the primordial chaos that birthed them. The idea that halos retain a memory of their origins isn't just poetic. It challenges everything we assume about how structure forms in the cosmos. Consider the early universe, a seething ocean of quantum fluctuations. Inflation, that explosive expansion in the first fraction of a second, stretched these tiny ripples into vast hills and valleys of density. Where dark matter pooled most densely, halos eventually coalesced. But here's the twist: not all those initial ripples were identical. Some regions were slightly lumpier, others smoother, like batter mixed imperfectly. If halos formed around these variations, their internal structure, the way dark matter particles orbit, their density gradients, even their shapes might still bear scars of those first imperfections. It's like examining a tree's rings to deduce the weather conditions centuries ago, except these rings are woven from gravity itself. One tantalizing clue comes from the distribution of primordial black holes, hypothetical relics from the universe's infancy. If these ancient black holes exist, they'd have acted as gravitational seeds, accelerating halo formation around them. Halos born this way might still harbor unusual density spikes or kinematic fingerprints near their cores, subtle imprints of their monstrous progenitors. Imagine stumbling upon a halo with a gravitational knot at its heart, a telltale sign that a primordial black hole has been lurking there for 13 billion years. But the memory might not always be so dramatic. Even without black holes, subtle differences in initial conditions could leave halos with distinct personalities. For example, halos that formed in regions where dark matter moved faster. Warmer patches of the early cosmos might today have more diffuse cores, their particles resisting tight clustering. Meanwhile, halos from colder, quieter regions could be denser, their particles settling into sharper peaks. These variations would be faint, but next-generation simulations might tease them out, comparing halo populations like astronomers compare star types. The implications stretch beyond theory. If halos remember their beginnings, mapping their present-day structures could let us peer backward in time, reconstructing the universe's infancy with unprecedented precision. A halo's spin, its subhalo arrangement, even its asymmetry, each could be a cipher waiting to be decoded, a message from an era before the first stars flickered to life. Yet the puzzle remains: how much survives the tumult of cosmic evolution? Galaxies merge, halos collide, and gravity reshapes everything over eons. Like a photograph left in the rain, the original image might blur beyond recognition. But if even fragments endure, they could hold answers to cosmology's biggest questions: how inflation unfolded, what dark matter truly is, even why the universe looks the way it does today. The halos we see now may be more than just invisible giants. They could be time capsules waiting for us to learn their language. There's an unspoken cosmic choreography at play between galaxies and their dark matter halos, a dance that should, in theory, follow predictable steps. When a galaxy spins, its halo ought to mirror that motion, their axes aligned like a perfectly balanced top. Yet the universe adores chaos, and countless galaxies flout this rule, spinning at odd angles or even counter to their halos entirely. This misalignment isn't just a curiosity, it's a clue to the violent, tangled histories hidden within these celestial structures. Picture a spinning coin tossed onto a table. The coin represents a galaxy, the table its dark matter halo. In an ideal world, the coin would land flat, its spin perfectly aligned with the table's surface. But give that table a jolt, say, a collision with another table, and the coin might wobble, tilt, or even flip entirely. That's the reality for many galaxies. When halos merge or endure tidal forces from nearby giants, their original alignment can be thrown into disarray, leaving galaxies spinning at oblique angles or even retrograde to their halo's motion. The cosmic ledger of these collisions is written in the skewed orientations we observe today. But why do some galaxies resist this chaos, staying stubbornly aligned despite the universe's turbulence? The answer might lie in their upbringing. Galaxies born in quiet cosmic neighborhoods where mergers are rare and tides gentle can preserve their primordial alignment for eons. Like a dancer who's never missed a step, their halos and stars move in harmony, undisturbed by external forces. In contrast, galaxies raised in dense clusters, cosmic urban centers bustling with gravitational interactions, often bear the scars of past encounters, their axes tilted like a picture frame knocked askew by a passing elbow. The wild card in this puzzle is baryonic matter, the ordinary atoms making up stars and gas. Dark matter may set the stage, but ordinary matter can rewrite the script. When galaxies form, their gas doesn't just passively settle into halos. It collapses, spins, and sometimes rebels, dragging dark matter along with it. Supernova explosions and active galactic nuclei can inject energy into the system, redistributing angular momentum and nudging galaxies out of alignment. It's a gravitational tug-of-war where visible and invisible matter constantly negotiate their shared motion. Then there's the role of time. Alignments aren't static, they evolve. A galaxy might start perfectly aligned, only for a close encounter with a neighboring halo to torque it off kilter. Over billions of years, dynamical friction could then gradually realign it, like a spinning top slowing until it matches its surface. The halos we see today are snapshots of this endless negotiation, some frozen in discord, others settling into sync. The implications stretch far beyond geometry. Misaligned galaxies challenge our assumptions about how angular momentum is distributed in the cosmos. They hint at hidden mergers, unseen interactions, and perhaps even exotic physics lurking in the dark sector. Every skewed galaxy is a Rosetta Stone waiting to be deciphered, a testament to the universe's refusal to follow a script. And until we crack their code, the dance between galaxies and their halos will remain one of cosmology's most beguiling performances. Dark matter halos have shaped the cosmos for billions of years, but nothing lasts forever. As the universe marches toward its ultimate fate, these invisible giants face their own reckoning. Will they evaporate into the void, collapse into monstrous singularities, or merge into ever larger behemoths? The answer depends on forces even more mysterious than dark matter itself, the relentless expansion of space and the enigmatic rules governing gravity's final act. Picture a halo today, a vast, shimmering network of particles, each tracing its own lazy orbit through the dark. In a static universe, this dance could continue indefinitely. But our cosmos isn't static. Dark energy stretches space-time like taffy, accelerating galaxies apart while leaving halos stranded in growing islands of isolation. Over trillions of years, this expansion could tear halos apart from the outside in. Particles on the fringes would drift beyond gravity's grasp, their orbits stretching until the halo resembles a ghostly haze, its structure dissolving into the cosmic background. This is halo evaporation, a slow fade into nothingness unless dark matter has hidden tricks up its sleeve. Some theories suggest dark matter isn't entirely collisionless. If particles interact even faintly, they could lose energy over astronomical timescales, sinking toward the halo's core like sand through an hourglass. The result, a catastrophic collapse where the central density spikes until, in the most extreme scenarios, it forms a black hole. Imagine a glacier melting inward until all that remains is a singular frozen drop. This wouldn't be an ordinary black hole. It'd be a primordial relic forged not from stars but from the invisible fabric of the universe itself. Yet the far future might hold stranger outcomes. In cyclic cosmologies, where the universe collapses and rebirths in endless cycles, halos could be recycled. Each iteration would shred them apart in a big crunch, only for their remnants to seed new halos in the next cosmic dawn. Alternatively, if dark matter decays, transforming into radiation or exotic particles, halos might simply vanish. Their gravitational scaffolding would erode, leaving galaxies unmoored, stars adrift like lanterns floating into the night. The wildest possibility, halos merging forever. In a universe without dark energy, gravity would keep drawing them together, building structures so vast they dwarf today's superclusters. Picture a cosmic matryoshka doll, halos nesting inside halos, their combined mass warping space-time into labyrinths of unimaginable scale. But even this empire of shadows wouldn't escape entropy's grip. Heat death spares nothing, not even darkness. What makes these speculations so thrilling isn't just their scale, but their stakes. If halos evaporate, they leave behind a universe where gravity's glue has dissolved. If they collapse, they might birth black holes that outlive the stars themselves. And if they merge, they sketch a future where dark matter reigns supreme long after light has faded. Each scenario whispers a different secret about dark matter's true nature and the universe's final breath, from the ghostly dance of misaligned galaxies to the vanishing satellites that defy our simulations. Each of these 25 mysteries peels back another layer of the dark matter enigma. The missing baryons, the too-big-to-fail paradox, the eerie spin of halos, they're not just puzzles to solve, but clues that the invisible universe operates by rules we've yet to decode. Every discrepancy between theory and observation, every halo that refuses to conform, whispers the same tantalizing truth. Dark matter isn't just hiding from us, it's challenging us to think bigger. Consider the bullet cluster, where gravity and matter part ways like actors in a cosmic magic trick, or Dragonfly 44, a galaxy that shouldn't exist yet floats defiantly in the void. These aren't anomalies, they're invitations. The Cusp-Core problem, the halo assembly bias, even the speculative filaments of dark matter hair, they all point to a universe far more dynamic, far more inventive than our textbooks dare to describe. And that's the thrill of it. Dark matter halos aren't just static scaffolding, they're living records of the cosmos's deepest secrets. Their shapes, spins, and struggles tell a story that's still being written, one where gravity's rules might need rewriting, and the very fabric of reality could be stranger than fiction. So here's the real question: which of these mysteries grips you? Is it the phantom galaxies adrift in voids, or the halos that spin against the odds? Dive into the comments and share your favorite cosmic head-scratcher. And if you're hungry for more deep dives into the universe's greatest enigmas, hit subscribe. The cosmos has plenty more puzzles waiting, and the next revelation might be just one click away.